Hey everybody, my name's Karissa and I work with Max Ogden. Hey, y'all in the back. Hey in the back. I'm about to give a talk. Hey, okay. My name's Karissa McKelvey and I've been working on this project for about 1.5 years. We are a nonprofit and we're funded by the Alfred P. Sloan Foundation. We're a 3-person team, although we're about to hire 4 more people, so it'll be 7 people. And it's all open source. We have over 800 modules on NPM, and everything's written in JavaScript or C. And we've been tasked with this question, to answer this question, how do we reproduce research today, and trying to make that better? And one of the things that I've been thinking a lot about is how reproducing research is actually more like collaborating on research. So when you create research, whether that's with someone in your company or your organization or in your lab, or whether that's someone from across the world because you published that research, you're actually collaborating with that person because you have to get their data and you have to know what they did. And you have to actually talk to them. And then what do you think about expanding research to data analysis more generally? And that's when the things start to get interesting, is when you talk about how we can collaborate on data analysis throughout all realms of life, every organization in the world. And that's the kind of thing that interests me, and what this project I think can bring. So what happens when you collaborate on data analysis today? What ends up happening is you start with like huge amounts of data that come from all over the place. Could be pictures of cats, pictures of the stars, sales records or whatever. I guess this is like an industry conference, so I have to throw that in there. But so you start with this, and then people end up, at least in universities and what the kind of research we did, we saw that people are actually putting this on a shared drive, and they're like hoping that nobody edits it at the same time, or pulls the wrong data, or accidentally deletes everything. And that's kind of like collaborating on big data today. And then you take this, gzip, and you put it into a Python script, which exports into CSVs, which you might put on GitHub or something, try and track it. Hopefully everything's fine, and then you have someone who comes along in R and like messes with the CSVs and outputs their own CSVs. And then you try to replicate that or reproduce that. It's really difficult, actually. And this is just a very simple pipeline from science, but we just saw in the last talk, these pipelines can get really complicated and involve proprietary services and all sorts of things. And so in the small use cases that I've been working with right now, we've just been using, really focusing on the use case of GitHub, where people are using GitHub to publish open data. And we're trying to see how that kind of fails or succeeds, and where we can come in to fix that. And a lot of the biggest problem we see is that Git does not do very well with very large data sets. As soon as you put anything over like 100 megabytes in there and start editing a lot, it just starts blowing up. And it takes forever to download. And you have to, with Git, you have to download everything in order to get any, even if you just want to see one row in the data set, you have to still download everything. It's a pain in the ass. Another problem is the good old git pull rebase origin master. Anytime you put someone who's familiar with R or SQL, or someone who's just learning to be a data scientist in charge of interacting with a Git repo, good luck and have fun. Even if you put a brand new software developer, a junior developer, and have them have a merge conflict, they're going to get in trouble. I've been using Git for 4 or 5 years now, and I still sometimes have to just, I have problems with it. So let's be clear about how domain experts aren't developers, and we shouldn't have them learn developer tools like Git. As someone who's really good at statistics, they probably didn't learn that much Git foo. And they're not going to be that good at it. They might be really, really good at data analysis, though. So we still want them around. They're studying the stars and the planets and math and shit, and we don't want to have them deal with it. What they end up doing is Dropbox. So Dropbox ends up being the place for us to collaborate on data. And I've been in this situation multiple times where I have to just put these CSVs into a Dropbox, and the R user comes and starts analyzing it, and all of a sudden we end up with 100 different data files, working model data, June 4th, 2012, or whatever, and then you have version 2, version 5, version 7. It starts to get unwieldy. And not only is Dropbox not really good at doing historical data analysis, Dropbox is actually not hackable. It has an API, but it's not open source. You can't actually integrate it into a workflow as easily as you want to. You can't modify it. It's not redundant. Like Git is redundant. You can really easily put a bunch of Git servers on a bunch of different places, and if one fails, it's not a huge deal. With Dropbox, it's still a centralized service. Free? Is it free? No, it's clearly expensive. Auditable? This is another problem with it not having this historical feature where you can't actually see where the data has come from. And it's not open source. So we need something like Git that still has these properties of being hackable and auditable and historical, but we need that for collaborating with data and data sets. And we also need something that's useful for building data pipelines. So Git itself is not actually that hackable. It's written in Bash. Try to put Git in the browser, for example, or something like that, and you start to have problems. Start to build something on top of Git, and you'll quickly notice that it's really hard. So we wanted to also make something that was developer-friendly. So let's take this example where I have a bunch of different files that I'm an R user, and I'm editing a bunch of different files that someone has given me. What I can do is I can create a dat link to this Dropbox folder, say. And this dat link is actually just a hash. It's a unique hash that is based on the data that was actually stored in those files. So if you actually go through each of these, we actually go through each of these files individually and produce a hash that is representative of those files. So if I change a single line in one of these files, I'm going to get a brand new hash. So then you can take a peer, or a computer, we call them peers, because there are no servers and clients in this model. This is a peer-to-peer model. So we take two peers that want to share data from one to another. The first thing they do is they talk to a peer introduction server, or any sort of way to introduce them to each other. Then they finally find each other. The peer introduction server says, hey, you have data that you want to give to this other person. And then those computers talk to each other and share the data directly from each computer to each other. So no data goes through a centralized server, which reduces the amount of round trips, makes it faster, reduces your bandwidth costs, et cetera, et cetera. It's actually really similar to BitTorrent. It's actually almost exactly like BitTorrent, but we don't use the protocol of BitTorrent. We actually just built a new, more efficient, for a variety of reasons, which I'll go into in a minute. So the way that we do peer introduction, BitTorrent just does the DHT, but we add DNS, MDNS, TCP, and we're going to add HTTP as well soon. But basically, we'll actually have a DNS implementation in Node.js that you can run as a server that will do DNS lookup and try and connect people together, which is really cool because it's a lot faster than trying to use the BitTorrent DHT. And you can use this right now. It's a module on NPM called Discovery Swarm. And then so the second thing that we do is really cool is we guarantee data integrity with Merkle trees. So it's just like Git or blockchains. I said the word blockchains. Guarantee data integrity with a decentralized model. So if we're looking at all of the different solutions that kind of are similar with data sharing and collaboration. The first here is BitTorrent on the left. BitTorrent is not open. So BitTorrent Sync is a proprietary protocol. And so I'm actually, even though the BitTorrent itself is an open thing, it's not open source and it's not very hackable in that way. Dropbox is obviously not open source. And then we can go down the list. So signable. This means that you can authorize. All of these allow you to authorize and sign a certain feed of data, which is really helpful for people if they want to make sure that you don't want some random person to edit your data. Historical, Git and DAT are both historical. Decentralized, Dropbox is clearly not decentralized, but the other three are. Content addressable, I'll get into that a little bit later, but basically, does anyone know what content addressable is? Okay, so only a couple of people. The great thing about content addressability is that you don't have to download the same data over and over and over and over again, even if the data changes just a little bit. Streaming, so something that is streaming means that you can get the data at the same time that someone is uploading it, and you can listen for changes on that data. So Git, for example, you have to wait for the entire commit to finish and be pushed to Git before you can like download anything, and you have to download everything at once. It's like an HTTP request. You can't just like get like the first 20 bytes and then the next 20 bytes and then the next 20 bytes as they're uploaded, for example. Indexable. So dat is the only one that we can actually give you a URL to a particular byte range inside of a file inside of your repository of your data set, which is a really cool thing that we think is it's really important for specifically data scientists that work with like huge data sets, and they just want to see like a row inside of one of the CSVs, but they don't want to download 3 terabytes. You can go read more about this on our blog. I just pushed a blog post about this. So dat data is different in a few other ways. It works in the browser, which I'm going to be demoing in a minute. It's entirely written in Node, which is awesome because we can do really cool stuff like decentralized applications where the person just has to drag and drop a file onto their web browser, and then all of a sudden it's into the swarm and someone can go get it on a server or someone can go get it somewhere else. So you can build really cool applications where people are just dragging and dropping files. And then they're in the system. The diffs are built for data, not for text files. So Git has their diffs specifically designed for text files, which creates a lot of problems, which is a lot of the reason why it's slow. Streaming and indexable byte ranges, which I already talked about. So that's a core theory. I'm going to show you this browser stuff because it's really fun. So this is something you can find on GitHub. This is called Hyperdrive. And this is the database that we're using in DAT. You can take a look at it, Macintosh/Hyperdrive. So what I'm going to do is drag and drop this CSV. So what it just did is it like hashed a file, and it gave me this hash. So let me open a new window. So it gave me this hash. I don't know if you can see that. So I can go to this link, and what it's going to do is it's going to connect to each other and starts downloading the data. So what I've actually done is served a data set from the browser to another browser without using any server whatsoever. So now I can go and click on this data, and I can see the first 5 rows of the data. What it actually did is fetch the first 5 rows. It didn't fetch all the data. It just fetched the first 5 rows. And if I used a bigger CSV, I could have like hit, load me the first 5 rows before it finished downloading, but I was talking too much. Something really cool that we also did was you can do this with movies. So a movie is a really good example of being able to stream something in real time. So I'm just going to show you that I'm not lying. So before this is finished downloading, you can see it's playing this movie before it finished downloading. Cool. So that's proof of concept. Now I can show you on so what I did here was do a dat link. This is our command line tool. I did dat link. Let me do it again. So what it does is it goes and it hashes the files. It took like, not that long to do 100 megs. And then I get this hash, which is actually dat ://. We're kind of experimenting with this because we're kind of thinking about like, what if, we had browsers that supported this? What would that actually mean? And it's kind of interesting to think about dat as like an upgrade on HTTP or something like that, where the data is always going to be there. And you can kind of reference it forever. And you can guarantee that it's the same data because it's the same hash. If any of the data changes at all, it'll be a different hash. So it's kind of exciting because HTTP, if you changed one letter, or if the server went down, you would never be able to get it again. But with dat, it's just like a new way to reference data that will always be available. So let me open up a new browser here, new terminal. So then I can download this data by just saying dat. And it says it's connecting, and then they're downloading to each other. And so now this one on the right becomes a server again. So if you wanted to put all the data on a bunch of different clusters, you could just say dat space the hash, and then it would distribute all the data to all the clusters and all the computers. And the more computers that are in the network, the faster it's going to download, because it's based on the same principles of BitTorrent. Are there any questions before I finish up and talk a little more about how it works? OK. So how do we do this part of like the streaming and the indexing? So what we do is we divide the files into small chunks that are unlikely to change when the file is updated. So for example, with Git, I'm going to use a Git example. Git also does a similar thing, but they do it really stupidly. So first you get one line per chunk with Git. So say I edit one line from world to monde. The other 3 chunks remain unchanged. So what happens is Git will just say, OK, so I'm going to send this one line of data. But what we really want is diffing made for data, not text. So what we use is rapid fingerprinting, which is, you can go look it up, content-defined chunking. There are some papers on it, which is you scan through the file and create chunks based on the actual file content. So and you can like tweak the parameters of like what kind of chunks you want. So say a new part is inserted into the middle of the file. We create a new chunk. The neighboring chunks are merged. And so then only those, so then you can like kind of ignore the other chunks, and you never have to go fetch those because they're the same. So it only fetches the new data. So you can get this on NPM as well. We did a Node.js implementation. But it has a C dependency. And actually, if it's something you're excited about, we would love someone to re-implement the C stuff in JavaScript. But right now, it's just in C with a JavaScript wrapper. So this reduces bandwidth use and increases the speed for the entire swarm, which is really exciting when you're starting to think about sharing terabytes and terabytes of data across lots of computers. So what's going to happen in the future? So we're going to have modules for doing backups on servers. So right now, if I'm sharing data from my computer and then I turn off my laptop, the data is gone, right? It's not available on the network. Even if I give that hash to someone else, if my computer is off, they won't get that data. So what we want to do is make it really easy for you to set up a server node. And then you can just say publish to that or push to that, and it'll like listen for changes and automatically pull your links and rehost them. The second thing we want to do is HTTP fallback. So that'll make it really nice if you want to use Google Cloud or storage or S3 or Internet Archive or something like that. So we're going to have like an archive format that you can put on an HTTP server. Then we're going to have a desktop application release to make it really easy for your friends who don't use the command line. And then we're going to have a background daemon manager, so you can have multiple DATs running on a single server without running like 20 different Node.js processes, because that's one of the problems right now is Node.js. Each time you run a DAT, it'll be 50 megabytes per server. So having a daemon manager, it'll be 50 megabytes for all of the DATs. You could run like 20,000 DATs on one server if you really wanted to. And then the last thing we want to do is open data scrapers, and this is what we just got $420,000 from the Knight Foundation to do. So what we're hiring 4 more people, and we're going to be turning all of the open data portals into DATs. So what we're going to do is every day we're going to scrape an open data portal, and then we're going to get their hash of that data from that day. And then we're going to put that into a DAT, which is going to be visible on a website, that's going to actually act like a torrent tracker. It's going to be like a torrent tracker for open data. And so then you can go and see like, oh, this zip file was put up yesterday. What did they change from the zip file from a week ago? Because in open government and open data in general, sometimes they're publishing like a zip file on an HTTP server, and you have no idea what they changed one day to the next. And so this will be really helpful for that particular use case, but also a lot of other really awesome use cases. So if you want to talk more about that, I would love to talk to you about that after this, because I'm going to be project manager on that project that's happening this year. Thank you very much. You can Find us on npm install -g dat, or look at Hyperdrive, which is the database we're using. And any questions are very welcome. Yeah.
So for your storage mechanism, you're talking about trying to store like CSVs efficiently. So I imagine that one's probably doing row-based chunks or column-based chunks. But how do you accommodate for? Will for example, if I do a column change, like I'm going to map these 3 columns, build a 4th column, is that going to touch every chunk in that file again?
It only touches the neighboring chunks. So that was that this.
Right. But if
yeah.
it's chunking by either column or row-based, right? One of those operations is probably going to be this.
Oh yeah. So we don't care what kind of data you put in. It'd be really cool if someone built something that was smart for CSVs, but we don't have something that's smart for CSVs.
It's not optimized on like a particular
No, it's like a parameter that you tweak. Do you want to do 128 bytes or whatever? Yeah.
Have you tested it for massive data sets?
Yeah, it works pretty well for like on the terabyte range.
Okay.
Yeah, it actually hashes things really fast. The only problems I see right now are like doing that in the browser. Like browsers are pretty bad at that.
You can fit a terabyte of
Good question though.
And you chunking happen in one physical node, meaning you are using P2P technology.
Yeah, the chunking, well, the original like hashing and chunking happens on one computer. Although it would be really cool, it would speed it up a lot if there was like a clustered version of that, but there's not. Yeah.
I've got some really esoteric data format, some crazy binary data format. Do I have to write a custom chunker for it?
No, because it just goes through and like literally looks at the bytes.
Can I access a part of the file? So at least
No, it's okay. Yeah. So that's one of the things that really differentiates us from Git, is that we built it with Node.js. So it's really easy to get, like, it's streaming by nature, and it's also indexable by nature. So you can say, I want a byte range of this file, and you can go get that. So even if the repository is like a terabyte, you can still say, I want the first row of that CSV, and you can get it.
you do any kind of index of chunks.
Yeah. Yeah, so when you actually do the chunking, it's actually doing a mini hash. Like, so you have a hash of, so in order to index it, you would say like a hash of a hash, basically. Or you would have a sub hash, I guess, or something like that.
So what I meant is that there are the scientific data forms, SDF, HDF.
Mm-hmm. I haven't tried it yet, but you could probably put one of them into this. You think of DAT more like a file system layer or something, like layer on top of file system. So you could put, if you're putting anything into a regular file system, you could just put it into DAT. It's just a list of files. So if HDF is just like a zip file, it's like looks like a file on the file system, I don't know. But if it's like a server, then it won't work right.
And will fetch parts of chunks lazily, or will fetch the file?
Yeah, it'll fetch lazily.
And you have some kind of read around, or
Sorry?
how do you predict which chunks to fetch first? Or you fetch only the ones which do last of
It will fetch stuff just from top to bottom, like in the way that it was first hashed, but unless you specify, oh, I want this byte range.
Is it a flat structure, or can you organize the files within that?
It's just like a file system. So there's actually, it originally is just like, it looks like a folder, directory with directories in it, like that. But there is an underlying module underneath Hyperdrive called HyperCore, which is more flexible. So HyperCore just stores arbitrary binary data. It doesn't assume that there's a drive. So Hyperdrive is like the thing that kind of assumes that there's a file system. So if you really wanted to just append, for example, here's the example. If you really want to just append, so you create a feed, and you can just append arbitrary blocks. And then on the other side, you can like download these blocks, and it'll just download hello and then world. Yeah.
Do you have a good way yet to like either visualize or print out like the DAG, the change history? Like if you have a file and you have 5 people contributing, you can see who kind of brought in, like with Git, right? With Git,
That's what I'm working on right now.
Okay.
Yeah. I'm actually calling it hypercommit. One of the things that we really like and appreciate about Node is that we really want to separate out everything as much as possible. So it's just like turtles all the way down. So that way people can be like, oh, I really like the idea of having a DAG of hyperdrives, but I don't want to use DAT. So you can go ahead and do that. So DAT itself is just like a command line wrapper around a database. It's really simple. But yeah, so this thing hypercommit is what I'm building right now, which is something called a hyperlog, which is the DAG part around a hyperdrive, which is the storage part. Like we have some users, but it's really all very super technical and super researchy right now on that end.
And you are not envision people actually can push compute to your node and then let you handle the prefetch and or data push to, or compute push to data.
No, that would.
Query.
I would love to get to that point. Actually, there's a. So we're a nonprofit right now, but I think there's definitely avenues, I think, for doing something like compute to data sort of services. So one of the things that we've been working on is called HyperOS. HyperOS, I think it's the IO. So HyperOS. So what we actually want to do is put containers, so not just files. So I'm talking about data files right now, right? Just like a file system. But if it's a file system, you could actually put in like a container. Why not? A container is just a list of files. So then think about that. If I have a container, a DAT container, and I put it to a server, the server says, okay, I want to run Python. What it'll first do is say, okay, I need bin bash. And so it'll go to the swarm and get the files it needs for bin bash. And then it'll go get the files it needs for Python. But then it won't download all the other stuff. So it'll be really, really, really fast to like mount and boot and run a container. So that's one of the things that we're really excited about, but we don't have funding for right now. So it's kind of just like an experimental thing.
Is there like Docker layers or something like that where you already have container constructs already done up for you?
Yeah, we aren't really, I mean, we appreciate Docker and like Docker, but we're more interested in like the peer-to-peer model, and so how we can like expand in the notion, because Docker containers, it's all based on like this, you download it and then you run it, and we're really interested in like, what if I want to stream it, or
I'm more meant for the executable component. Like you're talking about pulling in Python, pulling in Bash. Those things are like that's what that's good for, as opposed to I think yours is really good around the data that's going into that application.
right? I think we're talking about different things. So like you might have a Docker container that first sets it up, but then to send it to you, I might put it in a DAT and give it to you, and that would be faster.
Yes.
So we might do a Docker container once, but instead of giving you a Docker script, so then you run Docker on your machine, I only have to run Docker once, and then I've saved the state of my machine, and I can actually send that state to you as a list of files. Does that make sense?
I would think actually some application would like to query the chunks location, so I can, if I really have the opportunity to compute in your node together, coexist with you, I would love to know where should I push my compute to where the chunk actually is. Okay, so I can minimize the network traffic. Your bottleneck will be on the network if I have so many concurrent sessions. Right. It's bottleneck either on my client side, because I don't have enough bandwidth, or your side, your backbone doesn't sustain to that level I need. It's a big question.
Yeah. Are there any other questions? I think I have another minute or two. Cool. Well, come talk to me after if you want. I'll be hanging out for another 20 minutes or so.